United States Department of Agriculture.
Hi, I'm Tatum Katz, and I'm going to talk a little bit about how we can use data science to improve food safety. And I'm going to show you the ARS Grand Challenge as kind of an example of how we're using data science to improve food safety, specifically for Salmonella in beef production. I have a PhD in ecology and a master's in statistics, and my goal is to kind of combine these two fields along with all the data collected by my colleagues to kind of advance food safety goals. So my goals for you from this talk are, one, to learn about the Salmonella Grand Challenge, to understand what data science is, to understand what data science can contribute to a research program, and to think about how you can leverage data science in your own research and what challenges you might face in doing so. So first of all, what is data science? So I feel like this is a term that people are using a lot, and even I didn't know what it really meant, even though I was actually practicing data science. So data science is a very interdisciplinary or a transdisciplinary field, and the fields that we're combining are mathematics and statistics, programming, and domain knowledge. Okay, and so this is why I love this Venn diagram here, because we have mathematics and statistics and computer science. You add those together and you get machine learning. If you combine computer science and domain knowledge, you get things like software development. And if you combine domain knowledge and math and stat, that's where traditional research lies. When you combine all three of these together, you get data science. And so you know domain knowledge is kind of a weird term, but data science can be applied to a broad variety of fields. And so whatever field data science is being applied to, that's the domain. And so this is expertise in the field of application. And so for me, as an example, my domain is infectious disease ecology. And so the goal of data science, it has a lot of different goals and a lot of different tools. But the ones I want to highlight now are wrangling data from a high diversity of different sources, identifying novel insights to drive research forward. So data science is both hypothesis generating and hypothesis testing. So maybe you have a lot of data and you're not really sure what to do with it. We can use that data to generate hypotheses, and then we can help you collect more data to test those hypotheses. And the other big tool of data science is to create tools to help other researchers and stakeholders use their data effectively. And so this is really where kind of things like software development come into play, open source programming, and things like this. We want to make your data more available to you and those insights more available to others. So why are we talking about data science all the time? And so this is also because we're talking about fields that are very closely related to data science all the time. So things like machine learning and artificial intelligence. We're also closely related to big data, and visualization and communication of research is kind of a core tenet of data science. And so these things, we're collecting more data than we can ever digest into useful results. And so in order to actually start to digest those things into useful results, data science becomes really useful. The problem here is there's been historically a lack of expertise and training available. In the past, data scientists received their training by doing real-life problem solving instead of formal classroom learning. So a data science may come from, their background maybe in that domain, and then they add on math, stat, and programming skills on top. Or some data scientists start from a math, stat, or programming background and add domain knowledge on top. And typically this was done by just, experience, by collaborating, working with others, and learning kind of on the fly as you go. But as we have more data and thus more need to analyze that data, there are becoming more formal educational experiences that are available. So for example, I was the first cohort in my graduate program to be able to specialize in data science in my statistics master's. And so many of you are aware that there are data science boot camps out there, and things like this are becoming more and more common. So this is a really good time to take advantage of that fresh crop of data scientists who are getting these formal training experiences. And so this figure on the right here is a little bit outdated. It is from 2020. So things are getting a little bit better. But in 2020, this shows that 67% of companies were expanding their data science teams. They wanted to hire data scientists. And job listings for data science roles increased to 37% in the previous year. The problem here is there were 3 times the number of data science job postings than there were job searches. So there's kind of a gap between the need for data scientists and the available the availability of data scientists, but we're closing this gap, which is great. Okay, so now I want to shift gear a little bit and talk to you about the Salmonella problem. And so if you're watching this, you may already know that we have pumped a ton of money, investment, and research which has created a downward trend in Salmonella contamination on meat products. And so in this figure up on the top here, we're showing Salmonella contamination in chicken, beef, and turkey. And you can see that it's gone down quite a bit. However, if you look at the bottom figure, so the top figure is Salmonella on meat, and the bottom figure is Salmonella on people, basically. And actually, we have kind of failed to bring down Salmonellosis incidence in humans. And so depending on how you plot this data, there might be a slight increase over the last about 20 years. And so this kind of tells me that we need new approaches and innovative thinking to address this kind of ongoing challenge. Why do we have this gap here? And so here's where I wanted to introduce the ARS Salmonella Grand Challenge. So we're kind of envisioning the Grand Challenge as an umbrella for all ARS Salmonella research with the goal of improving our scientific impact, encouraging innovation and innovative thinking, and enhancing collaborative and multidisciplinary work. So we're bringing everyone together under this umbrella so we can all work together to solve this big problem. And so the ARS Salmonella Grand Challenge, even this slide is slightly outdated now. We are over 24 core members within the Agricultural Research Service and Economic Research Service, representing over 8 different locations across the US. We also have just initiated our computational postdoctoral community of practice. So a group of us postdocs meet and we discuss our computational concerns within salmonella research. We also have an industry advisory board representing the 4 major meat and poultry commodities across 4 different companies. And they help us figure out what are our research needs, what is important for industry. And we're currently expanding into additional collaborations at universities, industries, and other professional associations. And so in addition to this diversity of people, we also have a huge diversity of research happening. We have people coming from animal health, ecology, climatology and meteorology, we have genomics, microbiology, data science, and economics, all living together under this Salmonella Grand Challenge umbrella. And so our ultimate vision is to support stakeholders to implement affordable, effective, and data-driven strategies to address their salmonella food safety goals. And so we kind of have 6 major products that we want to produce. One is gold standard protocols that are going to be used across projects, and they're going to be publicly available. So other researchers or industry who wants to do their research knows what the gold standard protocols are. We're also bringing in some cutting edge data management platforms and ontologies so we can keep all of the data we're collecting across all these different research groups, keep it straight and keep it useful for our data analytics down the line. We're also implementing pilot studies to ground truth our research findings for application in real world systems. And that includes building cost efficacy models for industry so that we can show them not only will this application, help fix your salmonella problem, but it's affordable to do so. This is all going to be wrapped up together into decision support tools for stakeholders. We're going to build them with the stakeholders so that they're easy to interpret and use. And this will culminate also in demonstration products so that we can further show the value of these research findings in real world food safety systems. And so our Grand Challenge is organized into 5 different objectives, and this is kind of a schematic of how information flows throughout our team. So our tools objective is here to identify novel tools and standardized protocols. They pass that information to kind of our driver's objective here, whose goal is kind of look at the salmonella ecology. What are predictive reservoirs? What are drivers of salmonella in the on-farm pre-harvest system? That information gets passed to our interventions objective, who are developing mitigation approaches to address different scales of production complexity. So these are things like probiotics, vaccines, and other types of really creative strategies that we can use to control salmonella in the pre-harvest sphere. All this information gets passed to our decision support team, and so that's where I come in. And our goal is to use AI and machine learning to develop some easy to use decision support tools so that decision dashboard we want to produce to stakeholders. And perhaps most importantly is our communications team. So science cannot become applied solutions in a vacuum. And so the goal of our communication team is to help us not only communicate our research to stakeholders, but to take what stakeholders are asking us for and bring it back to us. So this is kind of our outreach and communications group. And so now I want to walk you through a case study where we have, I think, successfully been able to use data science to improve food safety. And so this work was done in collaboration with John Schmidt, Terry Arthur, and Tommy Wheeler at ARS U.S. Meat Animal Research Center in Clay Center, Nebraska. And so the original goal of this research was to identify pre-harvest predictors of salmonella-contaminated lymph nodes at harvest in cattle. And so these lymph nodes are a good indicator of salmonella contamination on final products, especially like ground beef and other things. They're a major contaminator. And so when this research, as we were kind of developing this project, we had a couple of working hypotheses. We have a lot of different sources of data and variation in the pre-harvest environment. We have management differences, weather and soil differences, and that may affect the pen surface that the cattle are living on. And we also hypothesized that pen surface may be predictive of what winds up in those cattle's lymph nodes all the way down the line at harvest. And so this is kind of our logical thinking schematic of how we approach this problem. And so as I walk you through this research, I'm going to walk you also through the data science process. So we're going to go from data collection to data cleaning to exploratory data analysis, model building, and model deployment. Okay, so let's start with data collection. So this project actually was ongoing even before I have joined ARS. So back in 2019, John, Terry, and Tommy collected some pen surface salmonella measurements. So how much salmonella was there and what kinds of salmonella it was. And they also collected management surveys. So we have a little bit of management information. And then of course, COVID happened, but then in 2021, they collected more pen surface salmonella samples and also took soil analysis. So what is in that soil that is underneath that pen that those cattle are living in? In 2022, they again collected pen surface salmonella measurements. They again did a soil analysis, and this time they also followed those cattle all the way through to harvest and collected lymph nodes from some of them. And then in 2023, this is when I came on and started analyzing this data. To me, as a data scientist, I was like, this is an obvious place to add in some weather data. So we were able to go back and collect historic weather data from each of these sampling time points. And here's what a little bit of this data looked like. So when I talk about varied data, this is what I'm talking about, right? We have measurements of salmonella in the pen surface. We have 4 samples per pen. We have salmonella on the lymph nodes from 1 year. We have 25 carcasses per pen, and there were 3 different types of lymph nodes collected. We also had the soil analysis. We get 1 value per pen, but there were well over 100 variables describing moisture, pH, minerals, metals, and salts in the soil. And what we learned is that a lot of the variables in this data set were actually really redundant. So that took a lot of cleaning. We also had a very limited amount of management survey data. It was 1 value per feedlot, but it told us really interesting things like where did the cattle come from, how dense were the pens, did they use probiotics, and how was their tylose in use. So we had some really juicy bits of information in our management surveys. And then when we went back and collected weather data, I collected it all from K-State Mesonet. So basically I matched feedlots to their nearest weather station and then used that weather station to say what the weather was at the feedlot. So we again have 1 value per feedlot, but we have this additional complicating factor that sometimes 2 feedlots were very close together. And so their closest weather station was the same. But this gave us variables like air temperature, soil temperature at different depths, solar radiation, wind, precipitation, all of these kinds of fun variables. And so all this data is coming across space and coming across time, and they have different experimental units. And so aligning this data was actually the bulk of the work for this project, and it often is when it comes to data science. Okay, now I want to talk about my favorite part, which I'm going to call EDA, which stands for Exploratory Data Analysis. And the goal of exploratory data analysis is to use visualization tools to learn about our data. So often we're working with such a large amount of data that it's hard to look at every single individual, observation. It's hard to look at the numbers. But if we can visualize the data, it's often a lot easier to do things like identify patterns, identifying errors, outliers, and issues with the data. And it can be hypothesis generating. So if we see patterns popping up in these visualizations, then we know we can chase those down with statistical tests later on. And I really like this figure from Towards Data Science. It shows you a little bit of what EDA might look like. Okay, so we might do things like plot the data distribution, so we know what kind of statistical models to use. We can look for missing data and try to understand why those missing data occur. Sometimes missing data is very informative. Maybe there are patterns even within those NAs or zeros that we can look at. We also do outlier looking, outlier searching. In this figure, that red dot is clearly an outlier. It's not always so easy. We look for correlation between variables, and so this is how we realized that the soil data set was actually very, very redundant, because we saw we had really tight correlation between like half of the variables. And so we were able to go from like 180 variables down to like 90, which that's pretty good. Again, we are looking for patterns. What can we model? We try to learn about the data types, make sure things are encoded correctly so the computer understands. Data visualization, my favorite, are box plots. And we check for data quality. We want to make sure that the data that we're going to model down the line is the best it possibly can be. Okay, and here's some problems that we caught during EDA. So one, after cleaning and combining all the data, we had 95 different variables describing just 24 observations or complete cases, if you're familiar with that term. So only for 24 individual experimental units did I have a complete set of data. And this is commonly referred to as an N versus P problem, where N is the number of observations you have and P is the number of parameters or variables that you have. And you want N and P to at least be equal, and often you want N to be much, much larger than P. And in this case, N is much smaller than P, so that's not so great. And then the second major issue is visualizing 95 variables is a lot. You know, if you imagine making different plots of each of those variables, that is not only computationally intensive, but time intensive. And so here are some of the solutions that we applied. So instead of analyzing all the variables together, because we simply couldn't, we analyzed the weather, management, and soil data separately to identify trends within each of those kind of contexts, and then modeled it together. So that helped us increase our N and decrease our P and figure out which of those 95 variables were the most important to include in our model. We also used some dimensionality reduction techniques to kind of squish our 95 variables into fewer variables. So doing things like principal component analysis, PCA, or CUR decomposition, some really helpful tools there. Another thing we did is we reclassified our outcome variable from numeric continuous to categorical. So we were initially modeling Salmonella index, so how much Salmonella is there. We changed that to whether the pen had high or low Salmonella. And that helped. We had a lot of high variance in Salmonella detection in these data, but by kind of binarizing that outcome, we were able to increase our signal and decrease our noise, which increases the power of our future statistical tests. Okay, and how do you visualize 95 variables? You just kind of have to do it. But this is where we can apply some computer science. I wrote programs to automate the visualization of these variables based on their data types. So I still have to look at every single plot to look for those trends, but I can really easily update those plots or change the data that are inside of them because I've written functions to automate the visualization. And here's just a little glimpse. If you work with me, unfortunately, I'm going to show you a lot of box plots. Like I said, those are my favorite. So for example, up here, we have the reclassified feedlots as high or low. And then we have what that Salmonella index was. So this actually worked out quite well. We wound up having our low pens having virtually no Salmonella, except for a few little outliers you can see here. And our high Salmonella feedlots, you can see the variance is really high, but there are large statistical differences between the Salmonella index between our high and low feedlots. And in this kind of multi-plot I have over here are some of the different soil variables and how those things split over high and low feedlots. And what you can see here is a ton of these variables will cluster around high or low feedlots. So for instance, phosphorus is much higher in those high Salmonella feedlots and lower in low Salmonella feedlots. So these are the types of trends and patterns, and things like outliers that we're looking for. Okay, let's talk about model building. So let's put this all back together. Okay, so we looked at the management data, and like I said, it was super limited, and we're actually still waiting on some responses. but it looked like in probiotic use may be a very important predictor of Salmonella in the pen surface. For the weather data, the ambient and soil temperature, as well as solar radiation, were really strong predictors of Salmonella in the pen surface. Looking at the soil data, many different soil variables, like I showed you in that last plot, like ammonium, soluble salts, and boron, were sort of weak to moderate predictors of Salmonella in the pen surface. And what we did show eventually was that Salmonella in the pen surface does in fact predict Salmonella load in the lymph nodes at harvest. So we do have this tie here, which makes our whole model nicely work. Okay, let's talk about some issues though, because I'm telling you a really nice story about putting a bunch of data together and getting some insights. But remember when I said we had 95 variables and only 24 complete observations? That was just not enough data to model this entire system together. You know, we can only model kind of each piece of that hypothesis tree. And we definitely have too few data to control for all the confounding factors. So like maybe two pens are together and now they're going to be spatially autocorrelated or things like this. So sometimes what you learn from EDA and model building is you need to go back and collect more data. Okay, but we are going back and collecting more data, and we're able to use some of those findings to show our stakeholders, look, we did find stuff. Give us the rest of that management data. Let us come back and collect more soil samples so we can flesh out this data set and start putting this model together. And so now I want to give you a little glimpse of the future of what model deployment for this work would look like. So I've talked a lot about building a dashboard for stakeholders. So based on our, some of our findings, this is what it might look like. For instance, we're going to ask you for the zip code of the feedlot, and we can use that to call data from a weather database from the user input. We can get, the dates that the cattle are in the pen, so we know when to call that data. We can, in this case, I've simply asked them, do you use a probiotic or not? And then if the producer has gone on and done their own soil analysis, then they can put in those variables for us. And we can take this all together, put this in the model, and get predictions from a model of what this feedlot salmonella risk might be. In this case, with these variables, the salmonella risk would be low. And then we can also, from kind of our interventions, provide recommended actions for our producers. So in this case, it was low risk, and we're going to tell them, hey, great, just maintain current conditions and keep monitoring these variables. Well, if you have moderate risk, maybe we would suggest to introduce a probiotic into the feed, and then you can monitor through time. What if you wind up with a really high risk pen? Well, maybe you want to send this lot to harvest last so they don't contaminate other products in the production facility. And so we want to keep this like a very simple, easy to interpret, kind of red, yellow, green recommender system. But this is kind of a glimpse of what that data dashboard might look like. So what is the value added data science? And I hope I've shown you kind of throughout this talk naturally what it will be. But we can use domain knowledge to enhance ease of communication between the domain scientists and the data scientists. We should be able to speak your language, and we can help issue spot in ways that traditional statisticians or mathematicians may not be able to. But having that classic math stat background helps us make sure our methods are quantitatively sound. Adding in the programming component helps us create reproducible results, and we can help deploy software for non-programmers, like that data dashboard. You don't need to know how to do the model. You just need to plug in the data points, and we can do the model for you. And here, I hope I've also shown you the ease of handling of some of that big data, so that high diversity especially, but other types of big data might be, you might have high volume, you have a lot of data, or you might have high speed data coming in real time that you need to analyze as it comes in. And so what are the takeaways for you today? First, I want you to know that data science combines mathematics, statistics, programming, and domain expertise to wrangle diverse data and give you novel insights with a focus on visualization and communication of results. In the Salmonella Grand Challenge, we use data science to identify pre-harvest predictors of post-harvest lymph node salmonella contamination in cattle. And we're going to use these findings to go on and collect more specific data. Right? We did hypothesis generation. Now we're going to go back, recollect the data so we can do hypothesis testing with better experimental design and more stakeholder support as well. And finally, the challenges we face are not unique to our system. How many of you have dealt with low data, diverse data, or an N versus P problem? And so this is kind of my favorite image here. We often feel this way in data science, but the goal is to wrangle that data and pull insights out of it, whether those are hypothesis generating or hypothesis testing. We want to make good use of the data that you have. Thank you so much.
USDA is an equal opportunity provider, employer, and lender.